Hello again, this is Professor Roman. Let's continue the lecture series Transition to Advanced Mathematics. We're talking about sets and multisets. Let us now take a look at the notion of disjointness. Two sets are disjoint if they have no elements in common. Here's the official definition. Two sets are disjoint if they have no elements in common, that is, if their intersection is empty. There's another definition related to this that I want to give you. It's not seen all that often, not as often as it should be. If A and B are disjoint, then their union is often called a disjoint union. And we will use this symbol, which is relatively common. It's like a union sign, but it's flat on the bottom. Straight line segments, 3 of them. You could read this A cup B, but I would just simply say the disjoint union of A and B. The concept of disjointness can be generalized to families of more than two sets. And the interesting thing about this generalization and others, oftentimes when you have a concept defined for two objects, two sets, there is more than one generalization that turns out to be useful. And that's the case here. So let's say we have a family of sets. It could be a set of sets, or it could be a multiset of sets. Doesn't matter. Then the family's disjoint if no element is in common to every member of the family, or in other words, the intersection of the family is empty. That's a more or less direct generalization of this. But another possibility, the family F is pairwise disjoint if no two sets in the family have any elements in common. So that would look like this. If I different from J, two indices that are distinct, then A sub I and A sub J are disjoint. So to illustrate, here is a family of sets, 3 sets. This family is disjoint because there is no element in common to all 3 sets. But it is not pairwise disjoint because, for example, the set 1, 2, 3 and the set 2, 9, these are not disjoint. Any family of sets that is pairwise disjoint will also be disjoint. If no two elements in the family have anything in common, then there's no common element for all the members. But the converse fails, as this example has just shown. So the concept of pairwise disjointness is actually stronger than the concept of disjointness. It's harder for a family to be pairwise disjoint than it is just to be disjoint. This isn't the only situation where a generalization from two objects to more than two objects has different important generalizations. Here's one you might already be familiar with. The integers a1 through an are relatively prime if they have no common factors other than plus or minus 1. Or put another way, the greatest common divisor of the integers is 1. On the other hand, these integers are pairwise relatively prime if no two of the integers have a common factor other than plus or minus 1. So that looks like this. I different from J in the index set implies that the greatest common divisor of AI and AJ is 1. So for example, the integers 2, 6, and 9 are relatively prime. They have no common factor other than plus or minus 1. But they're not pairwise relatively prime because 2 and 6 have a common factor 2. So as with disjointness, pairwise relative primeness is a stronger property than relative primeness. Now we come to an unfortunate little problem. It's not serious, but it's annoying. Not all authors define the concept of pairwise disjointness for multisets of sets the way we have done. Here is a family, a multiset of sets. Let me illustrate the issue with an example. Consider this multiset of sets. So there are 3 sets. A1 is 1, 2. A2 is also the set 1, 2. A3 is 4, 5. So this is a proper multiset because it has a duplicate. Ask yourself, do you think this family is pairwise disjoint or not? Why don't you, maybe you should pause the video and think about this. But according to our definition, the one I just gave, which is this, I different from J and I implies AI intersect AJ is empty, the answer is that these are not pairwise. This is not a pairwise disjoint family. The intersection of A1 and A2 is the set 1, 2, which is not empty. So this is not pairwise disjoint. And of course this applies to any multiset that contains a non-empty member, a non-empty set A, whose multiplicity is greater than 1. You're going to have this problem. There'll be at least 2 indices, I and J distinct, for which AI and AJ are equal to, let's call it A. So the intersection is A, and that's non-empty. So a multiset of sets that has this characteristic that it contains a non-empty element of multiplicity at least 2 cannot be pairwise disjoint. And that's okay. It doesn't bother me. But I guess it bothers some authors, because some authors give an alternative definition for pairwise disjointness to allow multisets like this one to be pairwise disjoint. And the alternative definition says that a multiset F is pairwise disjoint if it has the property that any 2 distinct members of the family are disjoint. Never mind the indices. If the members are distinct, they have to be disjoint. So if AI is different from AJ, then the intersection has to be 0. I didn't say I different from J. I said AI different from AJ. So that is different. This is our definition, and this is the alternative definition. Okay, and they are not the same as we have as we can demonstrate with this multiset here. According to our definition, this is not pairwise disjoint. But according to this definition, we have to look at distinct members of the family, not distinct indices. So there's only 2 distinct members of this family, this set, and they are disjoint. So this family, this multiset, would qualify as pairwise disjoint. Another way to say the alternative definition is to say the underlying set to the multiset is pairwise disjoint. Another way to say that is to get the underlying set, you cancel duplicates. So we could toss this one out. Now we have a set of sets, just two sets, and they are pairwise disjoint. Okay. So what to do about this inconsistency? Well, there's not much we can do except whenever you pick up a book or a paper, or you're having a discussion with someone else and they use the term pairwise disjoint family, you actually have two questions. First of all, can your family have duplicates? And second, if it can, what exactly do you mean by pairwise disjoint? And that's just the way life is. It's unfortunate that there is not different terminology to distinguish between these two definitely different definitions of pairwise disjointness. Okay, but it is very important to fully understand the distinction between the two definitions. Okay. And after you're finished with this class, if you prefer the alternative definition, you can adopt it as your own. But for this lecture series, this book, this class, we're using the definition I gave, which was the different indices have to lead to disjoint sets. Okay. Let's make a few remarks about the power set of a set, which we've already defined. It's if S is a set, the power set of S is the set of all subsets of S, a very important family of sets. I'll give you one fact that is occasionally useful. If A and B are sets, then A is a subset of B if and only if the power set of A is a subset of the power set of B. The proof is fairly simple. It would be a good idea for you to stop the video and try to prove it yourself at this point. Maybe I should have even left it as an exercise, but here is the proof. If A is a subset of B, then any subset of A is also a subset of B, which means that another way to say that is that any element of the power set of A is an element of the power set of B, and that is the definition of subset. Power set of A is a subset of the power set of B. For the converse, if we suppose that the power set of A is contained in the power set of B, then an element little a is in A. If an element A is in A, then the singleton subset, the set containing A, belongs to the power set of A. It's a subset of capital A, and that is a subset of power set of B, and so this singleton set belongs to the power set of B. In other words, it's a subset of B, which means its only element, A, has to belong to B. And so any element of A is an element of B, and therefore by definition A is a subset of B. Let us now take a look at the concept of an ordered pair. If you took a course in calculus or analytic geometry or something, you're probably familiar with ordered pairs of real numbers. That's how you denote the points in the plane. You denote them by ordered pairs. But where do ordered pairs come from? The ZF axioms, the ZF axiom of pairs tells us that if A and B are sets, then so is this doubleton set or pair AB. But this pair is an unordered pair. There's no distinction between which comes first and which comes second. There's no sense of order here between A and B. ordered pairs are not postulated by the ZF axioms. So we need to have a formal definition. Excuse me. Well, there have been several proposed definitions of ordered pair. But before I show you these proposed definitions and tell you who ended up winning at the end, we should really discuss the purpose of ordered pairs. As you know, an ordered pair is usually written this way with parentheses and a comma in between the elements. And the idea is that we want to be able to distinguish the two elements. And we do that generally by referring to one as the first component of the ordered pair, so that would be A, and B as the second component. So that while it's true for unordered pairs, these are the same when you swap A and B, for ordered pairs, these are distinctly different, unless, of course, A equals B. Otherwise, these are different ordered pairs. Also, a key property of ordered pairs is their equality. Two ordered pairs, A, B, and C, D, are equal if and only if the first components are equal, A equals C, and the second components are equal. That is a critical property of ordered pairs. One final remark before we look at the possible definitions is if we have two sets, one apparently has two elements, X and Y, the other has a single element, Z. If these are equal, then that tells us by the axiom of extensionality, which is basically our definition of equality of sets, is that every element in here is an element here and vice versa. That tells us that X, Y, and Z have to all be the same, which means X and Y have to be the same element. So this is, as a set, has redundancy. As a multiset, it's fine, but as a set, it'd be redundant. Now we're ready to examine some of the more prominent suggestions for the definition of ordered pair. And what's really interesting about this is not really the details of each definition or proposed definition, but what's really interesting about this is that we have four proposals made by four very brilliant mathematicians, and they're all different. And I'll tell you who the winner was after we look at the four proposed definitions. That is to say, I'll tell you the one that's been adopted pretty much universally. The first proposed definition came in 1914. The applied mathematician and philosopher Norbert Wiener suggested that an ordered pair AB, and I put subscript W for Wiener, that this should be defined as this set. It's a set with two elements. The first element is another set with two elements, the first of which is the set containing A, the second is the empty set, and then this one is a singleton set whose only element is a singleton set. This is a little complicated, you might say, but Norbert was a brilliant mathematician, so he didn't have any trouble with this at all. As far as the key property is concerned, of course, if A equals C and B equals D, then it's pretty clear that the ordered pairs are the same. You can replace A by C and B by D, and you'll get the ordered pair CD. Okay. That's going to be universally clear for all four of the proposed definitions in that direction. it's the other direction that takes a little effort. So suppose that we have two Wiener ordered pairs that are equal. So this horrendous looking set equals this one. We need to show that A equals C and B equals D. Well, what we know immediately is that each of these elements, of which there are two, must be equal to these, and they must match up. That's the axiom of extensionality. But the first problem to deal with is, what if the doubleton element here is equal to the singleton element there? Is that possible? Well, if that were to be true, then the remarks we made a few minutes ago would say that all three of these elements are the same. And that's a problem, because neither one of these singleton sets is empty. So this is not possible, which means the two doubletons have to be the same and the two singletons have to be the same. So this set has to equal this set, and this set has to equal this set. Well, if these two sets are equal, they have only one element in each case, so those two elements are equal. This equation, again, then we have to match up the elements somehow. The set containing A is not empty, so it must be equal to the set containing C. And so these two elements must be equal, A equals C. And this one tells us directly that B equals D. And so this key property is satisfied. Two ordered pairs are equal if and only if the corresponding components are equal. Norbert Wiener, by the way, is considered the originator of cybernetics, and he was instrumental in the development of modern artificial intelligence. He was very brilliant. He also told a friend of mine and his, we had a mutual friend, that my friend was not a first-rate mathematician, which I thought was a bit rude and also not really clear. My friend, who was a professor at MIT, was very brilliant. Anyway, another proposal for the definition of ordered pair came from the eminent mathematician Felix Hausdorff. And he suggested this one, which is a lot simpler than the Norbert Wiener definition. So the ordered pair AB is the set containing two sets, A1 and B2, where 1 and 2 are distinct sets different from A and B. So I would infer from this that if A were 1, we'd have to change this 1 to something else. Okay, so 1 and 2 here represent any two distinct sets different from A and B. That creates a little problem right there. It's a bit confusing. But in any case, as to this key property of ordered pairs, certainly again, if A equals C and B equals D, then these two are the same, A, B, and C, D. For the converse, if we have two ordered pairs that are equal, A, B, and C, D, then these two sets are equal. Now, since 1 and 2 are distinct from each other and from A, B, C, and D, we know that the element that contains 1 has to match up with the element that contains 1 over here. So A has to be equal to C, and similarly B equals D. So that was a lot easier. in this case. So we eliminated some of the complexity of the Norbert Wiener version, but at the price of a little funkiness with these sets 1 and 2. Hausdorff was a German mathematician who's considered to be one of the founders of a branch of mathematics known as modern topology, and who contributed significantly to fields of set theory, measure theory, functional analysis, and others. He was very, very brilliant. Unfortunately, he was forced to give up his academic position by the Nazis, and he was informed that he and his wife would be moved to a camp. And because of that, he and his wife and his sister-in-law committed suicide. So that's very sad. It was 1942. Another proposed definition for ordered pair was made in 1921 by a mathematician named Kuratowski, and he proposed this definition. The ordered pair AB should be the set that contains two sets, singleton set A, doubleton set AB. Now if A is equal to B, then we get something that looks like this, but this being a set collapses to this, which further collapses to this. Okay. As far as the key property is concerned, again, if A equals C and B equals D, then the two ordered pairs are the same. Conversely, if we have two ordered pairs under the Kuratowski definition that are equal, we get these two sets being equal. We need to deal with the case A equals B, in which case this side collapses to a singleton set that looks like this. So this other side has to also collapse, which means these two have to be equal, which means D has to equal C. Okay. So if A equals B, C equals D, and this equation looks like this, which tells us that A and C, first of all, it tells us the set containing A is the same as the set containing C, and then so A equals C, so all four are now equal. And this would work the same way. There's a symmetry here. If you start with C equals D, that will imply that all four are equal. So the only other possibility is, in a sense, the more difficult one, I guess, is that A and B are different and C and D are different. And we have to do the same kind of matching that we did in the first case, the Norbert Wiener definition. What happens if a singleton is equal to the doubleton? Well, if this happens, then A, C, and D are all equal. And under our assumption, that's false. So we don't have to worry about this strange matchup here. This set has to be equal to this set. The singleton sets have to be equal, and the doubleton sets have to be equal. Well, if the singleton sets are equal, then A equals C. And so we can replace this C by A, and if these two sets are equal, then B has to equal D. So the key property is satisfied by Kuratowski's version of ordered pairs as well. Kuratowski was a Polish mathematician and logician who contributed significantly to the fields of topology and other areas, publishing over 170 papers. During the war, World War II, he taught at the underground university in Warsaw because higher education for Poles, Kuratowski was Polish, was forbidden under the German occupation. So Kuratowski and Hausdorff suffered under the occupation during World War II. Hausdorff more so, I guess you'd have to say, than Kuratowski. There is a variation on the Kuratowski definition. It's a very slight difference. Let me go back here. Here's the Kuratowski definition. You have this A goes to a singleton set, and both of them go into a doubleton. This one, we just drop the extra braces around A. I don't know who proposed this variation, but it also satisfies the key properties, and actually, in a way, it's a little simpler, but maybe not quite as aesthetically pleasing of an element here and a set there, but whatever. Excuse me. I have to keep my herbal tea on hand. So in summary, we have 4 proposals for the definition of ordered pair. And they're all legitimate in the sense that they all have this key property that 2 ordered pairs are equal if and only if the corresponding components are equal. So who's the winner? Or maybe I should say, who's the Wiener? It wasn't Norbert Wiener. Excuse me. It's Kuratowski. His definition has become the standard definition of ordered pair. So here it is formally. If A and B are sets, the ordered pair AB is defined this way. It's the set with 2 elements. The first one is a singleton set whose element is A. The second one is a doubleton that contains both components A and B. The concept of an ordered pair can be generalized to ordered triples and so on. The idea is not very difficult. We just use the definition of ordered pair repeatedly. So for example, this ordered triple can be defined. First you form the ordered pair with the first 2 elements, A1, A2, and then you take that element and form the ordered pair of that with A3. And this can generalize. So once you've defined ordered n tuples, you can define ordered n plus 1 tuples in this way. I'm not going to make a fuss over this. This is actually what is called an inductive definition, and we're going to discuss inductive definitions in a later chapter. But this is enough said for this. Let's conclude our discussion of sets and multisets with the Cartesian product. This is something you may be familiar with from your studies in calculus or analytic geometry. If you have 2 sets A and B, then the set consisting of all the ordered pairs, A comma B, where the first component comes from the set A, the second comes from the set B, is denoted this way, A cross B. This is called the Cartesian product of A and B. And the order matters here. A comes first, B second. First coordinates come from the first set, second components, come from the second set. Cartesian products are named after a very famous mathematician from the 17th century, French mathematician and philosopher René Descartes. His motto was cogito ergo sum. Definitely worth looking up. It applies, in fact, to all of you who are studying this course. Now, of course, there's no reason why A and B can't be the same set, so A cross A is sometimes denoted by A squared. So it looks like this. Ordered pairs where both components come from the set A. But it is important to keep in mind, as I said, that if you switch order A cross B and B cross A, these are not the same, unless, of course, A equals B. That's because we're dealing with ordered pairs and not unordered pairs. The Cartesian product can be extended to more than two sets. For example, if we have three sets, then the Cartesian product A cross B cross C is just the set of ordered triples. First components come from A, second components come from B, third components come from C. And more generally, we can take the Cartesian product of any finite number of sets. And when the sets are all the same, we use the exponential notation. I didn't include this in the book, but the Cartesian product can be, in fact, extended to arbitrary families of sets, not just finite families. But it's not immediately clear how to do the extension based on the definition of ordered pair, ordered triple that I just gave you. The best way to understand how to generalize is to redo the definitions in equivalent ways and use functions. So I didn't want to go into that because we're not going to need it in this course. But it certainly can be done and should be done if you take a course in upper division, abstract algebra, topology, or other courses. You should see the generalization. But it's not something you need to worry about. Now you've got more important issues to be concerned with right now.